I will record the class as we go about the class every day. I can't guarantee that I do it every day because sometimes I forget or sometimes the sound doesn't work or whatever, so don't really depend upon it. But if you happen to miss a day, that's a place where you can go and figure out, okay, what did I miss? All right, you can also talk to your classmates and you can talk to me, but you know, I'll probably just tell you to go see the screencast. You can also see past classes, so if I've missed it that day, you can go back from the previous semester and get a catch-up sort of on what we did. Or if you want to just sit down and binge watch the entire class, why not? You could probably cover it in a weekend. Old quizzes and exams, I showed you all this last time. You can see all the old tests and the old reading quizzes to get a good feel. In fact, as you're reading through the chapter, why not print out some of these old quizzes and just test yourself on them as you go along? They won't be the same. Your reading quiz on Tuesday will be new and unique, but it'll be similar. Usually I just go through the book. Somebody have a book?
I'm sorry.
Yeah, I just grab it up your desk. So like I'll go through and let's see, what's a good question? I'm going to pick sort of basic things, like where they have definitions.
I have the green part included.
What's that?
The one where you take a green highlight.
Oh, you have that book? Okay, like here's one about Newton's third law. So it says that it turns out that if one object exerts a force on another, then the second object exerts a force on the first. These two forces are equal and opposites. So I would take something like that, like a basic definition, and I might ask, are forces equal and opposite for some multiple choice question? Okay? My point is, I'm not going to pull esoteric information out of the book. It'll be sort of big ideas from the book. Usually people do pretty well on the reading quizzes, and that's what I want from you. But you have to read the chapter beforehand. Kate.
How many, how many questions are on there?
About 10. Actually, 10, I think. I haven't made out Tuesday's quiz, so don't hold me to 10, but it'll be about 10.
Okay.
You'll have this equation sheet for everything, so don't bother memorizing the equations, and then here's the advice for making an A in the class. Okay? That was a quick rundown for you new folks, and just a reminder for you old seasoned veterans of physical science 101. Okay? Clickers. We do need clickers for this class, and I know some of you have them. Who does not have a clicker for other classes? Raise your hand, please. If you do not have a clicker. Oh, you ordered one? For another class? Or for this one?
She said she doesn't use it.
She just gave it to you. Okay. Raise your hands high. If you need a clicker for the class. That's fine. Just 3 of you? Okay. Well, I think I can handle that. So if you need a clicker, come see me. All right. We'll begin using them on Tuesday. We'll register and all that on Tuesday. Today we have some multiple choice questions, but because I didn't require you to have clickers this week, I'll just sort of do the thing. Raise your hand and give me the answer to that thing, which y'all are pretty funny, because some of you were non-committal. If you raise your hand and you are. I don't want to like that. Okay. That clear? Email from me soon about this. If you're not on Moodle, send me an email. Moodle? Are you on Moodle?
Yeah.
Kayla, you're not.
I'm not.
Send me an email. You have it. Anybody else not on Moodle? Awesome. It will be soon.
Okay.
Will be?
Yeah.
Yeah, it will be soon.
Is this syllabus up yet?
Huh?
Is this syllabus up yet? Or?
It's just on this website, but it will be on Moodle. This website will be on Moodle very soon. I apologize. I usually have all this up the week or two before. Okay?
You got bombarded. It's okay.
It's okay. Thank you.
I still have another teacher who doesn't have anything else yet.
They're required to put the syllabus up week 1. They're required to put the syllabus up week 1. If they're in my department, you let me know. Are they in chemistry? No. Oh, okay. All right. I don't know about those other people. All right, let's try these. We did unit conversions last time, and we did a little dimensional analysis. We talked about standards. We talked about the importance of having good standards, that the accuracy of your measurement is really intrinsically dependent upon the accuracy of your standard. And so, like, for example, if you want to test a big jet engine, how much force do you get out of a jet engine? Do you get 1,000,000 pounds of thrust out of a jet engine? Then you need to have 1,000,000-pound standard. And that's what they talked about when they created that 1,000,000-pound dead weight to calibrate jet engines. So very great accuracy, to 5 parts in 1,000,000. If you don't have that, then you don't really know how powerful your jet engine is. So that's why it's important for us to spend millions or even billions of dollars on defining a good standard, so that scientists and engineers and just people around the world, when they say, I have a kilogram, they know exactly what a kilogram is. Okay? It's very, very important. It is worth the billions of dollars that we spend worldwide to define our standards for mass, length, time, and other quantities that we'll talk about later this semester. Billions of dollars. Does it seem like a waste?
No.
No, because you fly in planes, you have cell phones, you have buildings, and those things are all dependent intrinsically upon our standards of measurement. Okay, let's try this clicker question, although no clickers today. The one on the left about Irene. When we have standards, we can use not sort of typical measurements, but here we can measure a building in Irenes. Irene is a person. She's a made-up person, but she is 2 meters tall. She's fairly tall. She's a little over 6 foot tall. And a building is 10 meters tall. And I want to know, how many Irenes is the building tall? If you were to use an Irene as a unit of measurement, how many Irenes would it be tall? All right, we'll take about 30 seconds. You can write in your book, please record an answer and commit to it. This is practice for the test, and you do need to be fast on the test, so go as quickly as possible. No, you don't have that page just yet. We'll get to chapter 1 next. W. What's up?
It doesn't have to do with this though, or not this question. Are we going to need to know like conversions like meters to feet?
I'll talk about it in just a second.
Okay.
The answer is yes, we'll talk about it.
Okay.
All right? What is your answer? I'll give you 10 seconds, and then I want you to raise your hand and do like we did last time. A, B, C, D, or E. All right? 1, 2, 3, go. Okay, awesome. The answer is E, that if Irene is 2 meters tall, then it takes 5 of her to make up a 10-meter building. And this one I think you can probably just think about. But the way that we would go through the process is that we would say 10 meters, and then we have our conversion factor. Our conversion factor is that 1 Irene, which I abbreviate IR, is equal to 2 meters. And so you see our conversion factor, it has a value, an intrinsic value that's equal to 1, right? Because 1 Irene is equal to 2 meters. So when we multiply this conversion factor, it's really like multiplying it by 1. Now the actual value is 1 over 2, but it converts that unit of meters to units of Irenes. And if I cancel out the meters, I'm left with 5 Irenes, like that. Okay? You'll have some simple unit conversions. They'll be something like that. Now, Vanessa, the answer to your question, she asked, are we going to have to convert, say, miles to meters or something from metric to British or British to metric system? The answer is yes, that you will have to do that. But you do not have to memorize the conversion factor. I will provide any conversion factor that is something like this, where you're going between systems. Now you do have to know your metric units. So like if I ask you how many meters is 200 centimeters, you do need to know how to do that. Okay, you do need to know what those metric prefixes are and how to convert from one to another. Alrighty? I think y'all can do that, right? How many meters is 200 centimeters?
Like
200 centimeters. How many centimeters are in a meter?
2 meters.
No. All right, let's go back to our, we did metric units, didn't we? I think we did. Oh, maybe we haven't gotten to it yet.
Yes, it's 2 meters.
You're right. Yes. Okay, maybe we ain't got to that. We'll get to it next. All right, let's go ahead and do this one on the right. Which of these is the unit for mass in the SI system for the convention? What is the unit for mass? Is it A grams, B pounds, C kilograms, or D slugs? Which is it? 1, 2, 3, go. 3 is right. When I say SI system, what I'm implying, at least in this class, is that we'll use the MKS system. Now, if you said A, I know what you were thinking. Because remember, within the SI system, there are 2 subsystems. There's the MKS for meters, kilograms, and seconds. And then there's CGS for centimeters, grams, and seconds. The standard one to use is MKS. So we'll always imply that I'm referring to MKS. Though, if you're in the health sciences, if you're an astronomer, if you're a chemist, you'll use the CGS system. I don't know why. But like CCs, right? That's a cubic centimeter. That's because health professionals use the CGS system. They use grams, they use seconds. Okay? As I said, we can convert unknown units. Let's just try this. I have 364.4 smoots. Just a little backstory. Anybody ever been to Boston? In Boston, across from the MIT, there's a bridge across, what's that river there? Is it the Charles River? Or the river that goes through Boston. There's a bridge there, and if you ever walk across that bridge, there are paint marks along the bridge, and it says 1 smoot, 2 smoots, 3 smoots. And it's because 100 years ago or so, some MIT students, some fraternity, one of their, I don't know, their initiation rites was to measure the bridge, the length of the bridge, in lengths of the shortest person in their fraternity. And the first year they did it was Oliver Smoot. He was the shortest person in the fraternity, and so he had the honor of measuring the length of this bridge across the St. Charles, I think it's St. Charles River. So if you go there, you can see the paint marks where they measure the bridge, and I don't know, it's a couple hundred smoots long. It's a fairly long bridge. I have a picture. I'll send it to you once. I took a picture of the smoot mark. Okay? He later won the Nobel Prize. Or was it his brother? I think they both won the Nobel Prize, actually. Or were related to it. So anyway, just a little trivia. So 364.4 smoots is 125 meters. How many smoots is 225 meters? The way we'd do this is we'd say 225 meters. We always start with our first quantity that we want to convert, and then we do our conversion factor. I want to set up the conversion factor so that the units cancel out. So I'm going to put 125 meters in the denominator. I do that because the meters then cancel out. And then I have 364.4 smoots in the top. And if I do that, I get look at you. 660 smoots. All right. Let's go ahead. Realize that we don't have metric conversions here, so we're just going to do a couple of metric conversions down here at the bottom too. There are 3 metric units that I want you to know. They're fairly common. That is milli, centi, and kilo. And these have quantities that are equal to 10 to the minus 3, 10 to the minus 2, or 10 to the third. Or if you don't want to write this in scientific notation or an exponential form, you could say 1 over 1,000, 1 over 100, or 1,000. So milli I will use to refer to small things like a millimeter, right? Or a millipede. It's supposed to have 1,000 legs. I don't think it really does have 1,000, but that's where that comes from. Centi, like a centimeter. In a centimeter, there are 100 centimeters in a meter. And then a kilometer is 1,000 meters. So a 5K race or a 5 kilometers would be 5,000 meters. So if I wanted to convert, say, a centimeter to meters, 220 centimeters equals how many meters? What I would do is I would first start with 220 centimeters, and then I would put in my conversion factor. 1 centimeter is equal to 10 to the minus 2 meters. So it would be 2.2 meters. It works exactly the same way as we did with the smoots. Okay?
Can we just move the decimal over two versus?
Absolutely. And that's the great power of the metric system, because everything is in orders of 10. Unlike in the British system where we have all these funky conversion factors, going from inches to feet, 12 inches in a foot. I mean, you have to divide by 12. Who can do that in their head, right? So that's the great power of the metric system, is that you can just move the decimal point. So I would expect some simple conversions like this too. I say simple. They're not simple if you don't know how to do them. And you won't know if you know how to do them until you practice them. Okay? Look back at the old test. You'll see some examples of where we have questions like these. Alrighty? How do you feel about that? Okay? Great. Awesome.
We can have chemistry class.
Yeah. So let's see. I think that I have questions.
You took it last year.
Let's do some questions. Look in the back of your book. It's in the very, very back. And you'll see some old tests. Let's try number 6. Exam 1, that's right. Y'all just try it on your own. Again, normally we would do this with clickers, but just try it on your own. Volume flow rate is a measure of fluid flow. It's volume per unit time. You express that in the SI system, what's it going to be? All right, just a few more seconds. Commit to an answer. I'll ask you to raise your hand. 1 through 4. 3, 2, 1. What you got? Some 2s and 3s. All right, 2 is the right answer. Cubic meters per second. Remember, SI system, we always assume MKS. All right, so 2 is, or B is the right answer, because volume is cubic meters and time is seconds, so that's going to be our volume flow rate. Now, as you know, in the health sciences, of course, they don't use that. They use cubic centimeters per second, cc's per second. That's how they measure fluid flow. Let's try number 7. This is a little trickier. Remember, with these, you'll want to put in the units for each quantity. V is velocity. Remember, that's meters per second. X is position. That's meters. And T is time. That's seconds. Oh, and also A I have here, which is acceleration. That's meters per second squared. I want you to find the equation that is not dimensionally correct. Put in the units for each variable, and the left-hand side should match the right-hand side. If it doesn't, it is not a correct equation. Just dimensionally, it's not correct. So it might take you a little longer. I'll give you about a minute or so. I see some pencils writing, okay? You're not going to know if you know it until you actually try it. So I want to see y'all thinking this through on the paper, thinking it out on the paper. Let me just show you all, if you're lost a little bit. Like, for example, the answer is not D, so let me show you with D that it is dimensionally correct. A is meters per second squared. V is meters per second. But it's squared, so both of those quantities are squared. And then X is meters, so I have it like that. And then I go through and I cancel out there. I have meters per second squared on both sides. So D is dimensionally correct, but it's not the right answer. Which of the other three is not dimensionally correct? Kate.
How did you cancel out the meters squared?
Oh, because I had a meter in the denominator. This X right here, I had a 1 over meters. Notice how I separated that equation when I wrote it. It just helps me to think about it more. I wrote it as V squared times 1 over X. Now when I write the V squared, it's meters per second, but it's squared. So it's actually meters squared per second squared. Meters per second times meters per second.
So you have to square both sides.
You have to know, you have to square V.
Yeah.
I could write it out another way. I could say meters per second, 1 over meters. And then this meters cancels with that one, and I'm left with meters over second squared. I know for some of you this might seem like a lot of math thrust on you on the very first day. Honestly, this class doesn't have a whole lot of math in it. This is the most complicated math that we'll get. And actually we'll look more at mathematical relationships than equations and calculations. All right, have an answer yet? You ready? 3 seconds, 3, 2, 1, raise your hand. All right, we got everything. Okay, that's fine. Let me show you. I think the answer is A. Okay, don't feel bad though if you didn't get the right answer. Meters per second on this side. Meters per second squared, and then 1 over seconds. You might have written that seconds in the numerator, but notice it's 1 over seconds. And so that's meters per second on one side, meters per second cubed on the other side. So that's not dimensionally correct. Let's go ahead and do these others. Kate, what's up?
So you multiply the other two.
I'm still completely confused.
I multiplied them.
So it's second squared plus seconds, so that would be seconds cubed.
Not plus seconds, second squared times seconds. I multiplied them, but division and multiplication are very closely related, right? So I multiplied meters per second squared times 1 over seconds. I said that A over T is equal to A times 1 over T. That's the same as saying A divided by T, multiplying it by the inverse of T. You can do this. I know that you can. It's important now because later we're going to be looking at different formulae. And while you're not going to be putting numbers into them, I'm going to ask you questions about how those variables are related to one another. And just being able to think about equations and how the variables float around inside those equations in your mind, it will help you a lot later. So that's why I want you to master this now, this idea of dimensional analysis. What are the units of x over v? Ooh, that's even trickier. X over V. Well, you know what the units are, because I've told you that that's not the right answer. But how do you get X over V to be seconds? Think about that. Does that blow your mind? X over V has units of seconds. Let me show you. X over V. Looking right here. I know the left-hand side is seconds, and so X over V better be seconds too, because I said the right answer here is A. And so B should be dimensionally correct. X is meters. V is meters per second. When I have a fraction in the denominator and I want to bring it up into the numerator, what do? For example, what is 1 divided by a half? Half goes into 1 how many times? 2. So when I divide 1 by a half, what I'm doing is I'm flipping that half upside down and bringing it up into the numerator. So I do the same thing here. I say meters times seconds over meters. That's just like saying 1 divided by a half is equal to 1 times 2 over 1. Okay? I know that you've had this. I know that some of you are freaking out a little bit inside, even though you're not showing it. But it's okay. You're going to be okay. You just need to practice a little. You had this 5th grade, you had it. I know you did. I know it's been a long time, and you probably haven't used fractions that much. But it's important for you.
Do you have a class after?
No, but I have welcome back there. But we can meet. We can talk if you need to chat. It's going to be okay. I'd really love to see y'all practice a little bit. Like spend a little time with it. Because we have some time before the next exam. And this isn't going to be on the quiz on Tuesday. Look through the old exams and practice them. That's really the best stuff. Like, it's in your brain. It is there. Like, I know that it's there. You just have to mine it out and bring it up to the top. Okay? I know you're freaking out a little bit. Don't freak out. It's not going to be a big issue. All right. You want to do another one? Oh, let's do the C. 2x over a. So I have t squared, looking right here. T squared, that's second squared. Remember the 2, I don't even worry about it. I have x is meters divided by meters per second squared. And so I'd rewrite that as meters times second squared over meters. Meters cancel, and I have second squared on both sides.
You can ignore any constants that are here.
Absolutely right, yeah. Ignore any constants that are in the equation.
That was messing me up on that one. Also,
That's what you were about to ask when I cut you off?
I was thinking about it.
Okay, all right.
I was gonna ask like about because like t and x variable is supposed to be variable, so if we just substitute in whatever units it would have to represent.
All right. How are we feeling? How about back here? You feeling okay back there? Yeah. Spend a little time thinking about it. What I would do over the weekend, or today or tomorrow, is print out some of those old tests and just try to pour through some of them. You know, like I said, you look at it for 5 minutes and have no idea what to do. But review what we did here, and then try to apply it to those other examples. And you will learn so much more in 10 minutes just by yourself than you will in an hour coming and talking to me. But if you need to come talk to me, of course, I'm here. But I find that when you struggle with things, that's when you learn the best.
What did you call this? Like,
Oh, dimensional analysis. We had a little section on it in the workbook.
Yeah.
Okay? Huh? And YouTube, yeah, but
Yeah.
don't spend a whole lot of time mining for YouTube. Come see me first. I'll help you. Look at the old tests. Look at examples of the old tests.
Those are answers.
They don't have solutions, but the correct answers are marked. Yeah. There's like a key in the back. Okay? All right. Let's do one more. Just for fun. That's what I said. Oh, look, here's this one. what are the units of this equation? Half of x times a divided by t. Put in the units for x, meters. Put in the units for a, that's meters per second squared. Put in the units for t, that's seconds. And then what do you get? Just start replacing the variables with the units, and then try to simplify it as much as you can. Remember, I like to separate out what's in the numerator, and then what's in the denominator I write as 1 over whatever the units are. If the denominator has a fraction in it, you flip it up and bring it upside down. Although that's not true in this case. Goodness, bless you.
Thank you.
All right, let's do about 15 more seconds. All right, 5 seconds, then we'll commit. 5, 4, 3, 2, 1. Come here first. Seeing 4s and 1s. Let's see what we got. So x is meters. A is meters per second squared. And remember, I'm going to write this t as 1 over t. So that's 1 over seconds. This is x, a, 1 over t. I separate out each variable. Then I can multiply these together, and I multiply these together. So that's meters squared per seconds to the 4th. What is that? Seconds cubed, I'm sorry. Whew. That's D is the right answer. Okay?
So you don't look at it as an equal sign at all?
This is not an equation, this is an expression. An equation has two sides that are equal to one another. A mathematical expression is just, I'm expressing something. I'm expressing half xa over t. Always break it down. That's right. Right? Just remember those couple simple things that if I have it, that constants don't count. If it's in the denominator, I like to pull it out and write it separately as 1 over whatever that variable is. And if it's in the denominator and it's a fraction, you need to flip it upside down. So 1 over a has the units of seconds squared per meter. Because a is meters per second squared. So you flip it when it's in the denominator. So there are really just a few rules. We wrote these down earlier. Constants don't matter. Separate out all the variables into separate parts. And if the variable is a fraction, units of a fraction, and it's in the denominator, flip them upside down.
I hate to do this to the class. But, I'm wish y'all work some more, honestly. What's an example of how to, like, flip a variable?
Flip a variable? Oh, we've done it. Let me check. Yeah, so, where do we do it? This one right here. That's the one you were saying, Vanessa? Yeah, so we had meters over meters per second. And this, which is in the denominator, when I bring it up into the numerator, I have to flip it like that. So if I have 1 over meters per second, that's equal to seconds per meter. Okay? We're going to move past this. I know that some of you are still frustrated, and some of you are like, oh, why are we spending so much time on this? But it is important. We have plenty of time in this class, so don't sweat it. Okay? Let's look at some other questions from this chapter. What about number 4? Length and what other two quantities make up the basic units for measurement in physics? I'll give you like 10 seconds. You should know this right off the top of your head. Length, what, and what? Mass and inertia, force and speed, mass and time, speed and time, or time and momentum. 3 seconds. 1, 2, 3. Show me your answer. Good job. You are amazing. Mass and time. C is the right answer. So on your test, you'll have some questions that if you've read the material and come to class, they're going to be giving questions, okay? I want that to be the case. Approximate height of a person. This just tests, do you know what a meter is? Or do you know what a kilogram is? Or do you know what a second is? All right, what is the approximate height of a person? How many meters? 1, 2, 3, go. Very good. So the answer is A, 2 meters. This is a meter. Meter's a little more than 3 feet. So a person, a pretty tall person is about 2 meters. Okay? That would be like a 6'6" person would be about 2 meters. Because a meter is 39 inches long, roughly.
That was 36.
A yard is 36 inches. Miss British system. But in the metric system, we use the meter, and it's a little longer than a yard. Okay? Yes.
When I was and he said, why is it British that we use?
Why is it British?
We use the English.
Yeah,
Why do we
is
use it?
called?
I don't know. I assume it just originated
Because he was
in
like
Britain.
in Britain. He's like they do like some type of weights like a stone. He's like I don't understand they don't use inches and all that there. So
Yeah, I mean, I think they use the metric system.
yeah.
Uh,
Why is it not American?
Well, I think it originates in Britain. I don't know exactly.
Oh, okay.
But I'm assuming that it originates in
Is
Britain.
it called the imperial system?
It does originate in Britain. Yeah, the imperial system.
Yeah.
Like
That is what you're talking about.
Yes. But as I think I told you last time, that the United States actually does use the metric system. I told you this?
Yeah.
That we signed on to the metric treaty about 100 years ago. And we use the metric system. It's just we convert everything to the British system. But really, all of our measurements are intrinsically based on big K, that kilogram prototype, or soon to be the watt pounds, right? We talked about that. On the frequency of the cesium atom, or the, what's the other one? The speed of light on the meter. All right. We have 7 minutes left in this class. Remember, I don't let you out early. Let's go back and look at chapter 1. I don't let you out early because we have valuable time and y'all spend lots of money to be here. So, we go until 8:35, right? Oh yeah, it is 8:50. I'm thinking Monday, Wednesday, Friday. Yeah. Man, you jokers. One of our faculty, honestly.
I wasn't gonna say anything. I was clapping.
One of our new faculty went into his class, and he asked a genuine question. He just didn't know when the class ended, just because he's new. And they told him it was like 8:15, but it was really 8:50 or 8:30 or like 20 minutes later. And you know, he's a nice guy. He doesn't think people will lie to him. And so he let them go. And then one student came forward, and told him that the class didn't end for another half hour. Isn't that terrible? I felt so bad. I was like, I'm really sorry. But he was fine. He just sort of laughed it off. He said he was going to make a joke about it today. You jokers. I know it was nobody in here. That's mean, isn't it?
Honestly, it's kind of sweet that one person went forward.
Yeah.
They only have that one person.
There's always one that messes it up, isn't there? All right. Newton's laws. There are 3 laws that Newton came up with. Isaac Newton, probably one of the most, I don't know, impactful scientists of the history of the world. For his laws of motion, but more importantly for something else that Isaac Newton did. Does anybody know what Isaac Newton did?
Invented calculus?
He invented calculus.
What?
Yeah. But calculus was such an important tool for the study of physics, for the study of engineering, for the study of looking at the physical world and describing it mathematically. So if we did not have calculus, then it would have We wouldn't be where, we wouldn't have this building. We wouldn't have everything that, like all the technology, the very basics of what we have, we would not have it. Watches, clothing, paper books like that. I mean, they would have archaic things. But not,
Stones that you carve into.
right.
I tell that to my brother and my son all the time.
Because of calculus?
Yeah, well, more about Isaac. Well, it's really with Isaac Newton invented calculus, among other things, and revolutionized the world.
Mm-hmm. Yes, revolutionized the world. Yeah.
Did he actually like discover gravity?
Well, he didn't discover it, he described it. Right? So people knew that gravity existed.
Oh yeah.
Right? And they knew that when you drop things, they fell.
I've heard that like he wasn't actually the first person to describe gravity.
Yeah, I'm not sure. He was the first to mathematically describe it.
Didn't apple fall instead? Isn't that like?
I don't know if that's true.
I think that's one of those that never actually happened, but it
Maybe so.
Caught, it is caught on for some reason.
Maybe
That
so.
sounds good.
Sounds good.
Be an awesome way to describe
Mm-hmm. But back to calculus. Like, even if you don't want to study calculus, you need to respect it, because it is a very powerful tool for scientists to use. But did you know, and this is just interesting, that somebody else discovered calculus at exactly the same time, separated from Newton by hundreds of miles? Did you know that?
Yeah, that's another thing, but I know there's always a whole big
Like
controversy or discussion about who actually should get the credit.
right.
Although, obviously, we don't get it.
Yeah. So Leibniz is the person. And so there's an idea in the world, I guess among sociologists, among scientists, that in the course of history that there are big ideas like calculus that come along, and it's like it's their time to come about.
Just aliens.
Some aliens. You see me roll my eyes. So there's this concept of having paradigms and paradigm shifts, and calculus was a paradigm shift. When we move from thinking about the world in one way to thinking about it in another way. So Newton, Leibniz, don't give them too much credit, because they lived in a time where we were right to discover calculus. And so, it makes you wonder, what are we right to discover now?
That's the thing.
Anytime. And there are some things on the horizon, and we'll talk about them, like gravitational waves. That might be the next big thing. They've discovered gravitational waves up in Livingston Parish, Louisiana, north of Baton Rouge. That might be the next big thing. That are gravitational waves going to shape the way that we think about gravity? We'll talk about that later. What's the next big idea? Like, one of you could be involved in the next big idea. I know you're all different majors.
There's some lady who just she was like the first guinea pig to for the new human genome, trying to extend lifespan and stuff like that. So maybe that could be it.
Maybe so.
Extending the lifespan.
Maybe so. Or it could be an idea in business, of course. It could be an idea in business or accounting. These paradigm shifts occur in all different fields. In education, there are paradigm shifts in education. There's a change about how do we think about the mind and how it works. Any of you could be involved in that. Isn't that exciting? So you could be part of changing the world. Think about that for a minute. Yeah. I hope an apple falls on your head. Isn't that cool?
Yeah.
He's changed the world. Isaac Newton changed hundreds of years to follow. He's in the right place, right time. Worked hard. All right. Anyway, his laws of motion. He's more famous for his laws of motion. The first law is the law of inertia. Inertia. Inertia is a measure of an object's mass. It describes an object's tendency to stay in its current state of motion. Kate said that our teacher in middle school teacher said that when you stop a car, that your body tends to keep moving forward. It moves into your seatbelt. That's because your body's in a state of motion that's moving, and your car wants to stop, but your body wants to keep moving because it has inertia. Inertia is this intrinsic quality of objects with mass. We don't really understand why objects have this basic quality, this basic attribute. But it's something that we're very familiar with because we live with it every day. But physically, we don't really understand why inertia is the way that it is. People a long time ago.
I think the next big thing.
Could be. People a long time ago, Aristotle had the view, and many of you also hold an Aristotelian view. You might not know it, but you do hold an Aristotelian view. He had the idea, not that this is true, but that objects always have a natural state. What would be the natural state of objects as far as their motion is concerned? What did Aristotle think that objects thought of their natural state to be what?
To be still.
To be still. Because you look around. When you look around, almost always things are at rest. And so Aristotle had this idea that objects in motion are unnatural. In fact, it was almost a spiritual idea where if you have something like if you shoot an arrow into the air, it's like you're ripping it from its natural state. And it just wants to return to that natural state. And so Newton came along, killing those paradigms, shifting those paradigms, and he said, no. Objects do not have a natural state. Objects will be whatever state of motion they're in, they will continue in that state of motion. If they're at rest, they'll continue to be at rest. If they're moving, they will continue to move forever. That's what Newton said. Unless you change it in some way, unless you have a force that acts upon it. This was groundbreaking to say that objects do not have a natural state, because that idea, that Aristotelian view, had held for many, many centuries, and it continues to hold today. Because, like I said, most of you have Aristotelian views. All right? Because you think that things have a natural state of rest. It's not true. So mass is a measure of inertia, and more mass, you have more mass, means it has more inertia, so it's harder to move, more difficult to move. So that's the first law, Newton's first law, the law of inertia. The second law is the law of acceleration. And the law of acceleration, first of all, just some basic definitions for things. Well, the law of acceleration is really an equation, and you've seen that equation. It's F equals ma. Pretty sure you've seen that. That a force is a push or a pull, is equal to the mass times the acceleration. So, like for example, going back to our first definition of inertia, that if I have a bigger mass and I want to accelerate an object, I need a bigger force. Bigger masses are harder to move because they have more inertia. So he described the second law, it sort of followed out of his first, as F equals ma. Actually, he didn't write it exactly like that. He did a couple things. We'll talk about this later when we get to momentum, but he really wrote it as A is equal to F over M. You don't need to know that, but it's the same, right? This is just a rearranging. You divide both sides by M. And then later, when we get into momentum, we'll talk about how Newton actually described this in terms of momentum. Momentum is the product of mass and velocity. Don't worry about that for now. We'll get to that. So some definitions. Net force. Net force is the vector sum of all forces. Pull on this ruler with about 2 newtons of force.
I don't know.
Wait, that's too much. A newton is about a quarter pound. So pull on it with about a half ton of force, not very much. A newton is a measure of force, and a newton, 1 newton is about a quarter pound. So, next time you go to McDonald's, fast food restaurant, and you want to get a quarter pounder, instead, say, no, I'm done with this imperial system, right? What are you going to ask for? A Newton burger.
It could fit in your food.
No, they're going to say, what? And then you're going to explain to them that we should be using the metric system. And the Newton is the measure of weight in the metric system. And don't you want to be part of a paradigm shift in the United States when we move everybody to the metric system?
Yes.
It would be nice if I could get that done.
Well, how many newtons I say? 2, right? 2 newtons. All right, now hold it over. You grab one side, and you grab the other. Now both of you pull with 2 newtons. So what? Okay. So Vanessa pulled with 2 newtons, right? And then Kayla pulled with 2 newtons. How much force total did they pull with?
0.
No, not 0.
Four.
They were pulling in the same direction. Y'all about to say it? 4, right. So 2 newtons in one direction, 2 newtons in another, they add up. That's a vector sum. So it's the vector sum of all forces. If I have an object, in this case it's me attached by the ruler. Sarah?
Would it still be a Newton if we got the quarter pound of cheese?
It would be a little more than a newton.
So it'd be a $1 cheese, right?
Right. A newton's about a quarter pound, roughly.
In the book, or I don't know which one, maybe you read the book or something already, said that it's an apple.
Yeah, about an apple. Small apple.
So, a vector is a direction, then?
I'm going to describe the vector in a second, yeah. So-
I was actually going to ask about the vector, but more of like, is it the same as a mathematical term for a vector?
It is a mathematical term, right?
So
Mhm.
it's the same as in math?
Yep, same as you learn about in math. A vector we use to describe a quantity that has both a magnitude and direction. We'll write that down in just a second. Let me write down what I'm going to write down here. So I have an idea in my head I want to get it to. So if we have an object and I apply 2 forces in 2 directions, right? This is Kayla. This was Vanessa. They were both pulling with a force of 2 newtons. 2 newtons. So the net force is going to be 4 newtons. That's all a vector is I'm just adding up forces. Now, what happens if Kayla and Vanessa and Stephen, right? You go by Stephen? Stephen was getting to this. What happens if Kayla and Vanessa pulled with 2 newtons in these directions? What is the net force on that object? It cancels out. Right. That's what you thought they were doing. In fact, the net force was 0 because I was applying a force of what on the meter stick? They were each pulling 2 newtons, and I had to pull back by 4 newtons. Okay? I know that the net force is 0 because of what? Why do I know that the net force on the meter stick is 0?
Because it's not moving.
Wait, go ahead. Because what?
Because it's not moving.
Almost. She said because it's not moving. That's sort of true, but not always true. You can have an object moving with no net force. Why do I know that?
Same number on each side.
No? Yes, but
There's no change in the state of motion.
yes. Almost. No change in the what? Or there's no acceleration. Yes. Because if you have acceleration, that means you have a force acting. That's Newton's second law. F is equal to ma. In order to have an acceleration, I have to have a total force that's not 0. But in this case, it had 0 acceleration, and so it had 0 net force. However, we will see that an object can have motion. It can be moving and still not have a net force, as long as it's not accelerating. Acceleration describes how the velocity changes. If I can have it move at a constant speed with no acceleration. Here, the net force, F net, is equal to 0. All right? I would describe this mathematically as the sum of all the forces is equal to 2 newtons minus 2 newtons equal to 0. Or let's change these just a little bit. Instead of 2 newtons, I want to put 3 newtons here, because I want to illustrate something to you. The net force in that case is going to be the sum of the forces is 3 newtons minus 2 newtons equals 0. So that gets us to some coordinate systems, and you need to know the notation that we have for coordinate systems. In a standard XY plane, this is the positive direction, this is the negative direction. This is the positive direction, this is the negative direction. This is our XY coordinate system. You live in an XY and Z coordinate system, but often when we're thinking about things on the paper, we just think in 2 dimensions, right? Not 3 dimensions. And that'll be the case here. Oh, it's not 0.
I was gonna say you lost me.
It's a paradigm shift. That would be 1 newton. This would be 0 newtons. Okay? Coordinate systems. We have chosen to define our spatial world, not our special world, our spatial world, like the space around us, by a right-handed coordinate system. And in a right-handed coordinate system, to the right is positive, to the left is negative. Up is positive, down is negative. This is in contrast to a left-handed coordinate system where these things are switched. Because we live in a world that loves right-handed people more than left-handed people. It's true. Like, I'm left-handed. I know.
Well, yeah, the desks are made.
Look, the desk, the notebooks.
I hate the spirals.
I hate the spirals. Hate them.
So sad.
It is sad.
I just use composition ones. That's all I can use.
I just don't even write. You just can't do it. Right? Okay. Anyway, right is positive, left is negative. Okay? Up is positive, down is negative. That's important when we're thinking about force vectors. Now, we can draw free body diagrams. I'm going to abbreviate it, FBD. If we have an object, say we have me, this is me holding that meter stick. There are multiple forces acting upon me. And in a free body diagram, I would draw all those forces. Okay? That's all a free body diagram is. I think about the situation and I label all of the forces that are acting. What are the forces that were acting on me when these 2 women were pulling on the meter stick?
Obviously gravity.
Okay, the gravitational force. That's my weight. So I'm about 700 newtons. Wow. Yes. Let me go on to the rec center and 700 newtons. That's sort of typical, right? 700. What other forces do I have acting upon me?
Atmospheric pressure.
Okay, that's small, but sure, there's atmospheric pressure. I'm thinking there are 4 forces acting upon me. Inertia is not a force. Inertia is an intrinsic quality of materials. They were pulling. Let's go ahead and start labeling some of these. So they were pulling. The different colors aren't working. I'm going to call this F pull. And then also, there's a weight. I'll call that FW. There must have been other forces because I was not accelerating. And I see no force to cancel out this force. and I see no force labeled here to cancel out this force. Which means that I must, if I only had these two forces, I would have accelerated down in this direction, but I did not. So I was holding it back. So where does that force originate from? Right. Exactly. So I pull back, and actually that force starts in my arms, but it eventually goes straight to my feet. So there's a force which was a frictional force between my feet and the ground. That you can't pull me because my feet stick to the ground. There must have been something else. So right now I got the two horizontal forces are canceling one another out. So I'm not moving in this direction, but I got a downward force. Why don't I just go crashing into the center of the earth? I got something pushing up on me, right? Right, what's pushing up on me? Man, we haven't gotten that word yet, but the earth, the floor, right? I got this great floor underneath me and it's pushing me up. So, it is called a normal force though, Paul. We'll get to that soon. Yeah, I'll go and put it there so you'll recognize it. It's called the normal force. Okay, that's a free body diagram. Then one other thing. If we have two forces, say a force here, I'll call it F1, and a force here, F2. These are both vectors, so I'm going to draw them with an arrow over the top. If I want to know the vector sum of those two forces, it's a little bit complicated. You have to use trigonometry, and you find various components of the forces, and we're not going to do that in this class. But I can draw the sum of these two forces. So they're both pulling in different directions, right? What is the direction of the net force? I have one force going in this direction and one force going in that direction. Where's the net force going? It's going right in the middle, right? You just did a vector sum. You just did, they do this in like calculus 3. You just did vector. All right? So anyway, that's the vector sum.
So even if we're pulling with two different forces,
Well,
I mean, it would still be in the middle, but...
Yeah, that's a good question. So this is F1 plus F2. And Vanessa said, what if you were pulling with different forces? Let me show you because it's kind of interesting. What if one of you was pulling with a really big force and one of you was pulling with a tiny little force? Then the net force would be closer to the big force than it is to the small force. So the net force would look about right there. Okay? That's a vector sum. I think we'll do some more vector sums later. But let's look at acceleration and velocity too. Because the Newton's second law, F equals ma, has a lot to do with both acceleration and velocity. And by the way, guys, so right now I'm following the book. And I follow the book. Chapter 0 is not in the book, but every other chapter that we do follows along in that book. And you'll see that all of these ideas are described in a little more detail in the book. So that's why it's so important for you to read the book. Read the book, okay? In fact, I think to each of these headings I just took from the book. Am I right about that, Annette? The headings are in the book? Yeah. Now, acceleration and velocity. Velocity is a change in position.
So the vector sum is the vector components are...
Did I leave something wrong? Yeah, that's vector sum. Yeah, vector components. If I have a vector right here, this is the vector. These are the individual components of that vector. Let me write that. This is a vector component. It's a component of the net force. third law is velocity is a change in position. It's over time. It's measured in meters per second. And acceleration is a change in velocity over time. And so it's meters per second, which is meters per second squared. The acceleration, if something's accelerating at 1 meter per second, that means if at first it's at 0 meters per second, how fast is it going after 1 second? Something is accelerating at 1 meter per second squared. At first it has 0 velocity. After 1 second has elapsed, what's its velocity?
1 meter.
1 meter per second. After another second, what's its velocity now? It increases in speed by 1 meter per second, so it goes to 2 meters per second. After 3 seconds, after a third second, it increases again by 1 meter per second. The acceleration describes how the velocity changes. Okay? Let's watch a video. I want to show you. This is Veritasium video. Y'all going to Welcome Back Day today? Yeah, the Chem Club is gonna have a table out. I think they're making liquid nitrogen ice cream. Whoop, whoop. They're making liquid nitrogen marshmallows. You can eat them and smoke comes out of your mouth and your nose. We're gonna try to fly our big solar bag. We have a 30-foot bag that if the conditions are just right, it will fly up in the air like a kite. We're gonna have a solar telescope. Come see the sun. Hopefully there'll be some cool sunspots. We're going to have a big mirror, and I'm going to set fire to the president. To a piece of paper. With a big mirror like you used to do with your magnifying glass, kind of. But I have a big mirror. It's really cooler.
Where is this?
It's in the quad.
What time is it?
10:30 to 2. But most of our activities are going to happen in the first hour and a half or so. So y'all come on out, look for the chem table. Oh, here it is. So this is going to talk about the laws of motion, but he describes them in an incorrect way. Actually, he's going to describe the laws of motion in an Aristotelian way, which is the way that most people see the laws of motion. Now, the third law, which I haven't told you yet, we'll talk about next time, says that if I have a force, then I have to have an equal and opposite force. So, for example, I'm 700 newtons. How much force is the floor pushing up on me? It has to be the same, otherwise I'd be scooting towards the middle of the earth or flying up off the surface of the earth. It has to be exactly the same. So he'll talk about these incorrect laws of motion. Let's watch this. First, let's watch this one-a-day women's vitamins.
350 years ago, Isaac Newton came up with 3 laws of motion that govern how everything moves. There are 3 pretty famous laws of motion. And they're not very complicated, but if I told them to you as clearly as I can, you would think that you're understanding them. But I think you wouldn't. And the reason is, everyone has